crystal vibration. The physical properties of a solid can be roughly divided into those that are determined by the electrons and those that relate to the movement of atoms about their equilibrium position. Properties like thermal properties, specific heat, thermal expansion, sound velocity, thermal conductivity. The hardness of material is also determined by the movement of atoms about their equilibrium position. The division of solid properties into atomic dynamics and electronics properties is qualitatively easy to justify. The motion of atomic nuclei are, due to their high mass, much slower than the motion of electron. If the atoms are displaced from their equilibrium position under any external force or thermal energy, the electrons adopt a new distribution. The electron system, however, remaining thereby in a ground state, if the initial position of the nuclei are restored, then the energy expended is recovered and there remains no excitation of the electron system. That's why here we are taking some approximation that the atom is vibrating to and fro, up and down from its equilibrium position. We can say it is a elastic wave that vibrating from its equilibrium position. The material shows elastic behavior in atomic level. The bonds between atoms are elastic. The atoms act as if they are coupled by a springs. Thermal energy or outside forces causes the atoms and molecules to oscillate. A packet of these waves can travel throughout of the crystal with a definite energy and momentum. And the quanta of that definite energy of elastic wave is known as phonon. Let us consider a elastic vibrations of a crystal with one atom in the primitive cell. That is vibration of crystal with monoatomic basis. Consider a elastic vibration of a crystal with one atom in the primitive cell. We want to find the frequency of an elastic wave omega in terms of propagation vector k and lattice constant c. The mathematical solution is simplest in the 100, 110 and 111 propagation direction in cubic crystal. Here is a cubic crystal. Here is the origin 0, 0, 0. Here is the 100 plane. The face diagonal is 110 plane and the body diagonal is 111 plane. These are the direction of the cube edge, face diagonal, body diagonal. When a wave propagates along one of these directions, entire planes of atoms move in phase with displacement either parallel or perpendicular to the direction of wave vector. We can describe a single coordinate un, the displacement of the plane n from its equilibrium position. The problem is now one-dimensional. For each wave vector, there are three modes as solution, one of longitudinal polarization and two transverse polarization. Here is the picture from Kittel that vibration of atom is in the direction of propagation vector is known as longitudinal wave and the vibration of atom which is perpendicular to the direction vector is known as transverse wave. Consider a set of atoms of mass m distributed along a line at all points separated by a distance a. Same, which are separated by a distance a. And they are vibrating with a elastic constant. Let's see. This is the nth plane. This is n minus 1th plane. This is n plus 1th plane. And this position of that mass is un. Position of that mass is un plus 1. And displacement of that mass is un minus 1. We assume that the force on the plane n is caused by the displacement of the n plus 1 proportional to the difference between un plus 1 minus un of that displacement. So let the force F1 is acting on between this and force F2 acting on that mass due to this. Okay. So the force F1 is proportional to difference between two displacement, that is un plus 1 minus un is nothing but F1 is equal to force constant C un plus 1 minus un. Similarly, F2 proportional to difference in between this displacement is equal to un minus un minus 1. That implies Ft is equal to some force constant un minus un minus 1. The net force acting on that m is F net is equal to F1 minus F2. F1 minus F2. That implies F net is equal to C common out taken outside un plus 1 minus 2un plus un minus 1. So F can be written as m d square un by dt square. It's nothing but C un plus 1 minus 2un plus un minus 1. Equation number 1. Let the solution of second order differential equation is, let the solution is un is equal to u0 some amplitude, some phase part e to the power I omega t plus kx. X is the total distance, which is nothing but n. Okay. So un is equal to u0 e to the power I omega t plus k n. Similarly, un plus 1 can be written as u0 e to the power I omega t plus k n plus 1 a. It's nothing but u0 e to the power I omega t plus k n a e to the power I k a. So un plus 1 can be written as nothing but un e to the power I k. Similarly, un minus 1 can be written as un e to the power minus I k. Putting un minus un plus 1 and un in the above equation 1, we will get m d square un divided by dt square is equal to c un plus 1 is nothing but un e to the power minus I k a minus 2 un plus un e to the power minus I k a plus un plus 1 is the un e to the power I k. Okay. Again d square un by dt square we can write by second derivative of un, we'll get I omega 2 times, that means minus omega square, that means minus m omega square is equal to c e to the power I k a minus 2 plus e to the power minus k a un taken outside. Here minus omega square m omega square un. Okay. So we'll cancel the un in both sides. That will omega square is equal to minus c by m, means e to the power I k a plus e to the power minus I k a minus 2. Nothing but minus c by m is nothing but 2 cos k a minus 2. 2 taken outside, that is 2c by m, 1 minus cos k. Omega square can be written as 2c by m, 1 minus cos k is nothing but 2 sin square k by 2. So omega is nothing but under root 4c by m sin k by 2. This is the dispersion relation of phonon in monoatomic basis. Then omega is minimum when k is equal to 0. That is omega minimum is equal to 0. Omega is maximum when k is equal to plus minus pi by a. That is omega max is equal to under root 4c by m. K is equal to plus minus pi by a is nothing but boundary of first Brillouin zone. The first Brillouin zone boundary. So we can draw omega versus k diagram. This will be k, this will be omega. First Brillouin zone is plus pi by a, this is minus pi by a. And the minimum value is 0 at k is equal to 0. Okay. So maximum at plus minus pi by, it will be maximum value omega, maximum value of omega is under root 4c by m root over. So at k is equal to plus minus pi, it will be maximum, and k is equal to 0, it will be minimum. So the graph will be okay. We know group velocity v is equal to d omega by dk. This is nothing but a by 2 under root 4c by m cos ka by 2. By taking group velocity is equals to 0, or what value of k the group velocity is equal to 0, let us see. By equating 0 we will get cos k by 2 is equal to 0, that is equal to nothing but cos n pi by 2, where n is odd integer. So k by 2 is nothing but n pi by 2. So 2 get cancelled. So k is equal to n pi by a. Is nothing but plus minus pi by a, plus minus 3 pi by a, plus minus 5 pi by k. This is nothing but boundary of first Brillouin zone. At boundary of first Brillouin zone, the groove velocity equal to 0. That means groove at k is equal to plus minus pi by a, that is boundary of first Brillouin zone, the groove velocity is equals to 0. That means no transfer of energy. That means no transmitted wave also. No transmitted wave at first Brillouin zone boundary. That means no transmitted wave means there is a standing wave in which alternate atoms oscillate in opposite phases. This situation is equivalent to Bragg reflection of X-ray. When the Bragg condition is satisfied, a traveling wave cannot propagate in a lattice. But through successive reflection back and forth, a standing wave is set up. So at k is equal to pi by a, we can write in place of k, there is 2 pi by lambda is equal to pi by a. So pi get cancelled, lambda is equal to 2a. This is the minimum wavelength lattice can carry energy. I will show you a graph in which the wave is represented by a solid curve conveys no information not given by the dashed curve. Only wavelength longer than 2a are needed to represent the motion. Okay.